All right, folks, we have our quarterlies this week. I put together this review sheet for you to sort of help you prepare, but you may have come across some questions that you think, well, I don't really know how to do that. So I made this video here so that if you're stuck on anything, you can just watch it through, and I will explain the questions for you. I'll go over them. I'll answer them for you. The point that I want to make here is I want to make sure you know how to do it. That's the key to this. So I understand I can't be one-on-one with everybody every day all the time. So hopefully you find this video helpful. Okay, so number one, the table shows the speed of a car on the road. Over which interval is the speed constant? So the table shows us different times and the speed of the car at those times. So at 8 o'clock, it's going 75 miles per hour. At 8:30, it's going 45 miles an hour, right? And so on. So interval, the word interval is sort of ranging between times. So for example, 8 to 8:30, that's an interval of time between those times. From 8 to 8:30. Now you'll notice that over that interval, the speed went from 75 to 45, meaning that over that interval, it was decreasing, right? Now we're looking for an interval in which it's constant, meaning that the speed doesn't change. But let's just go through everything just to make sure you understand all the intervals, all the different types of increasing, decreasing. So let's look at the next one, 8:30 to 9:30. Between 8:30 and 9:30, the speed went from 45 to 55. So over that interval, the speed was increasing. From 9:30 to 10, we went from 55 to 60. So that's another increase in speed over that time. And then from 10 to 11:30, we went from 60 to 60. So this right here is where our speed remained constant. It did not go up, increase. It did not go down, decrease. It stayed exactly the same. So when we're answering this question, we're going to say, okay, well, the speed remained constant over the interval. And part of my notation here, from 10 o'clock to 11:30. Over that interval, the speed remained constant. And I know this because it started at 60 and ended at 60, right? Started at 60, ended at 60. Oop, I forgot to write 60 there. Started at 60 and ended at 60, meaning obviously the speed's not changing. It's not going up, not going down. Remain constant. All right, the function f of x equals 50x represents the number of steps a person walks per minute. How many steps does the average person take in 7 minutes? So if you're just, a random person just walking for, minutes at a time, if they walk for 7 straight minutes and they're taking 50 steps per minute, well, how many steps does that person take over that period of time? Now, I'll just explain the notation just so if you see this again, you'll know what it means. F of x, okay, that means the same thing as y equals. F of x equals is the same thing as y equals. So don't get that too bothered. It's just function notation. We're going to talk more about that in the future for sure. But it means the same thing like y equals. But what it means in this case is total steps. Total steps after x minutes. All right, where then the 50x, of course, x represents just how many minutes we've walked, okay? So f of x is the total number of steps after however many minutes, and x itself is that number of minutes. Okay, so we're working, if we walk for 7 minutes, right, then we're doing 50, we're just plugging in 7, 50 times 7 to get our answer. So 50 times 7, that is, 350? 350 steps. There you go. And it's just like that. That's your answer. That's how many steps they've walked. All right. Number 3, we didn't talk about this too much. We definitely talked about it a little bit, but we never really got too specific with it. Okay. So here we have an equation, and all these steps down here is that equation being solved, but it's using specific properties in order to solve it. So if you looked at this problem, the first thing you would do is you would subtract 7 on both sides. And that's exactly what they've done here. You see it's the exact same problem, right? This equal to 13, this equal to 13. But you'll notice that the new feature is they're subtracting 7 on the left and on the right. So because they're subtracting a 7 on both sides, what they're using is the subtraction. This is hard to do because my tablet's like standing up vertically. So I apologize, my handwriting's a little bit sour. All right, oh man. Subtraction. Property of equality. All that means is that the subtraction property of equality just says that you can subtract the same number on both sides and everything is still equal. So you can clearly see, hey, you know what? We're subtracting 7 here, or the problem is subtracting 7. So they're using the subtraction property of equality. They're subtracting on both sides. Now, on the next step, right, all they've done is they've canceled out these 7s and they've simplified 13 minus 7 to make it equal to 6. But you can see, there's no more 7s on the left side and the right side just turned into 6. So they didn't really do any math properties. All they're really doing is simplifying, right? So we call this equivalent equation, or you can just say simplify. Okay, we use the word simplify because it's an easy term, but you'll see the word equivalent equation pop up sometimes. That just means the same thing, okay? That all they've done was simplify. Now you'll notice on the next step, right, they're getting rid of this 2 in the denominator, and what are they doing to do that? They're multiplying 2 on both sides. See that? It's the same equation as before, but they have times 2 on the left and times 2 on the right. So, if the first one was subtraction property of equality because they were subtracting on both sides, this one's going to be the multiplication property of equality. Multiplication. I'm just going to abbreviate POE for property of equality, just so I don't have to write it all out. Okay, but you can tell that they're multiplying on both sides, so they're using the multiplication property of equality. So these terms are pretty easy to remember. And then again, they just simplified, right? On this step here, all they've done was cancel out those 2's, and they simplified the 6 times 2 into 12. So when they're just simplifying, right, they're not adding on both sides or multiplying on both sides anymore, right? We're talking about just this step, right? All they've done was simplify. Then we're just going to write equivalent equation again. And again, that just means the same thing as simplify. On the next to last, right, you can see, okay, they would get rid of the minus 5. They would add 5 to both sides. And that's exactly what they've done here. They got plus 5 and plus 5 to the both sides of that equation. So guess what? They're adding on both sides. You know what we're going to call that? The addition property of equality, because they're adding on both sides. And then I guess the last step, all they really did was simplify again. So you could probably say equivalent equation. But it is our final answer as well. So I'm just going to make a note of that over here on the side. That is our final answer. Okay, so basically it's pretty straightforward. If they subtract on both sides, it's subtraction property of equality. If they multiply on both sides, it's multiplication property of equality. If they're adding on both sides, they're doing addition property of equality. Of course, if they're dividing on both sides, it'll be the division property of equality. All right, so just be aware that you already know the distributive property as well. It didn't occur in this problem, but you know what distributive property looks like. So that's another one to keep in mind if it shows up. Distributive property, if anyone is a little bit confused, is something like, okay, if you have 4 times x plus 3, and you have to distribute to both terms, so you get 4x plus 12, right? That's a distributive property. We did not see that in this problem, but be just aware of it because it could happen somewhere else, Okay. So number 4, Michael is 31 years old. 5 years ago, he was twice his brother's age. How old is his brother now? Okay, so He's 31 years old now, right? 5 years ago, he was twice his brother's age. So 5 years ago, Michael was 26 years old. You with me? Now, 26 is twice his brother's age. So 26 is double 13, right? 26 is equal to double 13. So his brother's age at that time was 13. So 5 years ago, his brother, this is not our final answer, by the way, I'm just pointing this out, his brother was 13. So you understand how I got that, right? We'll spell this out one more time, right? Michael's 31 now, but 5 years ago, meaning when he was 26, he was twice his brother's age. So if he was 26 and he was twice his brother's age, then his brother was half of 26, right? His brother was 13 years old. How old is his brother now? Remember, his brother was 13 5 years ago. So add the 5 years back, and his brother is now 18 years old. So our final answer is actually 18. Okay. Kind of an interesting problem. I don't really know if it's really much of a math problem. I mean, it kind of is, but I don't know what standard they're trying to get at, but it's a good problem. Number 5, an online music website subscription costs $10 to purchase to keep the subscription running. It costs $3 each month. Which equation represents the cost C for months of the subscription? So our equation here, we're going to have C, the cost, the total cost of the subscription, total cost of subscription is equal to the $10 purchase fee. And then it says an additional $3 per month, so plus 3M. So C represents the cost, M represents the number of months subscribed. So there it is. It's the cost is equal to $10 plus $3 per month. There's your expression. A little more straightforward than you would think. So don't overthink that problem. I think a lot of times students just tend to overthink it and get it wrong for that reason. But there it is. And I used C and I used M because that's the letters they told me to use in the problem. They said let cost equal C, right? And let M be months. All right, number 6. Stephen lives 5 miles from work. Now, this is a very interesting one. It's one that I can really explain to you guys. Okay. The graph below shows Stephen's route, where T represents the hours after he began his route, and D represents the number of miles from his house. So right here, this is going to be hours. In this section over here is going to be miles. I apologize for not having that written down on your paper already. Okay. So basically, like what this would say here is if I go to this point, that means after 1 hour, he's 5 miles away from home. Okay, that's what that means. So we're going to select all the statements that correctly describe the graph. So Stephen worked for 3 hours. How do we know this? Well, remember, this is his distance from his home over time. So here, this part of the graph where it's going up, he's walking away from his house, right? 1 mile, 2 miles, 3 miles away from his house, all the way until 5 miles away from his house, right? After an hour, he's 5 miles away from his house. Now, for the next 3 hours, from 1 to 4, for these 3 hours here, he is the same distance away. He hasn't moved, right? He's stopped somewhere and he's been there for 3 hours. So this is probably his work, right? So that makes this first statement true. He was at work for 3 hours. We can see that because his position was stationary for 3 hours. Now, Stephen took 1 hour to walk to work. So that's true as well because you can see that right here, right? His distance is increasing over time. It's always going up. He's not stopping at all because he's constantly moving further and further away from his house. And that length of time took 1 hour because after 1 hour, he stopped walking, right? After 1 hour, right? This is him walking. After 1 hour, he stayed the same again. So yeah, that's true as well. It took him 1 hour to get to work. Stephen took 2 hours to walk to lunch. Okay, so remember he's walking to work here, he's at work here, and now it looks like he's walking to lunch here, and then this is probably his lunch, right? Where he's chilling there for an hour. That's probably where his lunch is. So right here is his walk towards lunch. Now that is from 4 to 5. That's only 1 hour long. So this says it took 2 hours to walk to lunch. I would say that that's not true. I would say that's false because according to this graph, it looks like he's only walked for 1 hour, right? From hour 4 to hour 5. It's only 1 hour of walking. Now it goes up to, he went 2 miles. We could say that, right? Because going up to, he's going 2 miles, 1 mile, 2 miles, but over the period of time, it's only 1 hour walking. Stephen went out for lunch for an hour. We've already kind of mentioned that, right? This is where he's at lunch because he's stationary. He's not walking anywhere. His distance isn't going anywhere. He's staying where he is, and that's for an hour. So we can presume that that's his lunch hour. So this is true. Stephen stopped for an hour on his way home. So after he leaves lunch, he's walking back towards his house, and right here he stops. So in that period of time he stopped for was just 1 hour long. So yeah, he did stop on his way home for an hour. That is true. Stephen went to a place for lunch that is 8 miles from his house. So remember, his lunch was here, but if we look at the miles, that's 7 miles away from his house, not 8, based on the graph. So that is false. Stephen was gone for 12 hours. Well, not really, because he left at hour 0 and he came back at hour 10. So he was really only gone for 10 hours, right? So this is false as well. But that's how you read that graph. I hope that helps you interpret it a little bit better. It certainly can be challenging, but I think once you get it, you really get it, and it sinks in. So if you still have questions about that, just let me know. I'll be happy to explain it to you in class. All right, Gio and Ruben are solving math problems as they study for a math test. Giovanni noticed that he had finished solving 5 problems in the same amount of time Ruben solved 7 problems. If they kept this pace, as Ruben finishes his 35th problem, how many problems will Giovanni have solved? So basically, in the period of how many minutes? Oh, it's just the same amount of time. Yeah, we don't know how long they've been working, but they know that over the same period of time, right, Gio solved 5 problems when Ruben solved 7. If they keep at the same pace, if they double the amount of time, Gio will be on problem 10 and Ruben will be on problem 14, right? Gio's always going to do 5 problems in that period of time, 7, and Ruben's going to do 7 in that period of time. Okay, they're going to continue to go up at the same pace. Let me make this, I'm going to put this sideways instead so I can see a little better. Gio, Ruben. Okay, I'll pause it for a second. All right, sorry about the pause there. Hopefully you didn't lose me there. Okay, so remember, in the same period of time, Gio will solve 5 problems, Ruben will solve 7. We don't know how long it is, but it doesn't matter. We just know how many they solve over that time. If they do the same period of time, Gio will do another 5 problems, meaning he'll be at 10, and Ruben will do another 7 problems, meaning he'll be at 14. Right? Again, over the same period of time, Gio will do another 5 problems, which makes his total now 15, and Ruben will do another 7 problems, making his total 21. Again, same period of time, Gio will do another 5, making his total 20. Ruben will do another 7, making his total 28. And then again, same period of time, Gio will do another 5 problems, putting him at 25, and Ruben will do another 7 problems, putting him at 35. Now, the problem is, when Ruben's finished his 35th problem, what problem will Gio be on? Well, when Ruben's at his 35th problem, Gio is going to be on his 25th problem. So our answer is 25. Gio will have solved 25 problems. So you see what I did there is I just kind of went up the constant amount. Gio's pace is 5 problems over that interval of time, and Ruben's pace is 7 problems over that interval of time. So once Ruben got to 35, Gio would have been at 25. So you see what I'm saying? So that's kind of how I would do that problem. It seems a little easier to iron out that way. Okay, number 8. Ashton budgeted $700 to spend on vacation to Paris. He knows that he will spend $40 a day on food. What equation represents the amount of extra spending money, M, that Ashton will have after D days of his vacation? So his extra spending money, M, we're going to start it like this. M, his extra spending money, is equal to, now he starts off with $700, right? But because he's spending $40 a day, he's going to lose $40 per day. And so however many days he's on vacation, we take that, we do 40 times that many days, because that's, his total spending on food. Subtract that from 700, we could see what's left over. So this is our equation. This is our equation that represents how much extra money he has after D days of his vacation. So remember, he starts at 700, but he's spending $40 per day. So for example, let's just say, just to help me understand it a little bit, let's say his vacation was 5 days long. If his vacation was 5 days long, then the amount of extra money he would have would be, let's see, 740 times 5 would be like 200. So if his vacation was 5 days long, then he would have $200 just for the food. He would have to spend $200 on food. But 700 minus 200 means that he would have 500 left over as extra spending money. Okay? That's kind of how that expression would work out, that equation would work out. But I think the question only asks for the equation, so just this here. A bag of popcorn at a movie theater ranges in price from $5.50 to $8.50, and drinks range in price from $3.75 to $5.75. Which inequality represents the least amount of money, M, a person spends to buy one bag of popcorn and one drink? So if you're going to the movie theater and you want popcorn and a drink, but you want to spend the least amount of money possible, then you're going to choose the cheapest popcorn, which the cheapest popcorn would be $5.50. Right? And you're going to choose the cheapest drink because your goal here is to spend the least amount of money possible. The cheapest drink starts at $3.75. So you'd have to spend $5.50 for popcorn and $3.75 for drinks, meaning your total would be just adding those up together. So that means you would spend, what's that, $9.25? Okay, definitely going to rule out C and D here. So the amount of money we spend, we cannot spend less than $9.25. It's physically impossible because if we get the cheapest stuff, then the least amount of money we can spend is $9.25. So the amount of money we could spend could be more than or equal to $9.25. So it's A rather than B, because what B says is that we could spend less than $9.25, but we can't. Because we're said we are going to buy, this person needs to buy a bag of popcorn and a drink. And if they're going to buy a bag of popcorn and a drink, then the lowest amount of money they're going to spend is $9.25. Meaning that they can spend more than $9.25 or equal to $9.25, which is option A, not option B. So just be very careful with how you pick those. Now, the second part of this, it's not really number 10, but I guess you can think of it as the second part of this. Which inequality represents the most amount of money a person needs to buy so this is like the most expensive option. So it's kind of the opposite. For the most expensive option, you're choosing the most expensive popcorn, which would be $8.50, and the most expensive drink, which is $5.75. So total that up, and that is $14.25. So remember, this is the most you can spend. Okay, you cannot spend more than that because it doesn't cost more than that. So you would spend less than $14.25 or equal to $14.25. You can't spend more. So the reason why it can't be D here, you can't spend more than $14.25 because you've already bought the most expensive stuff. You're only buying one bag of popcorn and one drink. Yes, you can spend more if you buy more than one popcorn and more than one drink, but it says you're only going to buy one popcorn and one drink. $8.50 is the most you can spend for one popcorn. $5.75 is the most you can spend for one drink. So you cannot spend more than $14.25 for just one bag of popcorn and one drink. So that means the total we can spend would be less than or equal to that amount. We cannot spend more than that. We must spend up to that amount of money. So anywhere slightly less than it or equal to $14.25. All right, that's it for this review video, guys. I hope you find that a little bit helpful. If you have questions, do let me know. I'll see you guys. Good luck on your quarterly, by the way. See you guys. Bye.